We are going to talk about the construction of suffix tree in O of n time using Ukkonen's algorithm. Suffix tree is a very useful in numerous string processing and computational biology problems. It is not easy to implement code to construct suffix tree and its usage in many applications. Here we will discuss Ukkonen's suffix tree construction algorithm. We will discuss it in step-by-step detailed way and in multiple parts from theory to implementation using an example. I'll try my best to explain suffix tree construction. Before we dive directly into an example, let us keep some points in our mind. There are 5 pointers which we need to keep in mind before we begin construction. That is a remaining pointer which keep track of remaining suffixes. Initially, we will set it to 0. Then active node, the node from which the construction is happening. Active edge, the edge of the node to which we should proceed. Active length, for an active edge, how much we should move forward. So it describes from how much forward we should go to any character from an active edge. And it basically tells us how many character suffixes are made till now. Initially, we will set it to -1 and we will increase it gradually. And there is also one thing called suffix link, which we will create between every node. So this is also a link to cross from one node to another, which will just help us cut the time. And also to keep in mind that we are going to append a $sign at the end of every word, so to convert our implicit suffix tree to a true suffix tree. So these are the 3 main rules which we should keep in mind before construction of Ukkonen's suffix tree. Rule 1 is if after an insertion from an active node that is root, active length is greater than 0, then first, active node is not changed. Second, active length is decremented. Third, active edge is shifted right. So here rule 1 says that if there is a node, first, before beginning construction, we should add character to end of every leaf node. Rule 2 says that here we will take into account not only the newly created internal nodes, but also the internal nodes from which we made an insertion. After an insert from the active node, which is not the root node, we must follow the suffix link and set the active node to the nodes it points to. If there is no suffix link, set the active node to the root node. Either way, active edges and active length stay unchanged. In a plain English, I would say that rule 2 just simplifies that. If the character which we are at is not right next to the current pointing nodes, then we create a new leaf node for that character. And rule 3 is a stopping classifier, which says that if we find the next character to be the required character, then we stop the construction and boom, and we increment our I pointer to a next character. So let us dive deeper into the construction. So what we are building is basically like a search tree. So there is a root node, edges going out of it leading to new nodes, and further edges going out of those, and so forth. But unlike in a search tree, the edge labels are not a single characters. Instead, each edge is labeled using a pair of integers, that is from and to. These are pointers into a text. In this sense, each node, each edge carries a string label of arbitrary length, but takes only O of one space. So we have taken a string Mrs. C, and as we have discussed about the pointers before, I have mentioned all the 5 pointers. So initially we have set the remaining pointer to 0. Node, edge, and length are yet to be defined, and end is initially set to -1. So if we start from the first character and we point a pointer I, let us assume, is pointing to index 0, representing M. As M is not in our tree, we first make a root node. Let's make a root node R, and we can either go left or right to make M. But initially, if we first we should always increment our remaining by 1 and end by 1. We're gonna increment it. And we can either go left or right. Let us go left. Label it M. And as we have seen before, we are gonna label it the starting index and the ending index. And starting is 0 and end is still the ending of the string. Now as we have satisfied all the character suffixes of the first character, that is M, we are gonna, according to rule 3 classifier, we are gonna decrement our remaining by 1. Is 0. Now always as our remaining has reached 0, we can increment our I pointer. So I is now pointing to I, which is at index 1. So according to rule 1 classifier, we're gonna add I to every leaf node we have in our tree. So we're gonna append I at the end of our first leaf node, and as we do not have I, we're gonna make a new leaf node for I and label it 1, comma, n. Now as we have reached rule 3 classifier, that is we have reached our character which we were looking for, we can now increment our I pointer. Also we forgot to increment the end character, end pointer. Increment it to 1 from 0. And as the remaining is 0, we can increment our I pointer, which is now pointing to S at index 2. Now, according to rule 1 classifier, we're going to append S to every leaf node we have in our tree. And also, we're going to increment our remaining by 1. It is 1 and end by 1. Now at the root node, as we do not have any direct character suffix S, we're going to make a new leaf node for that. It is going to be S, which has label 2, comma, and 2 is the starting index of S, and n is still the end of the word. Now as we have reached our character S, we're gonna decrement our remaining by 1, which will be 0. Now as the remaining is 0, we can increment our I, which is pointing at S again, but at different index, that is 3. So according to rule 1 classifier, we're gonna append S to every leaf node we have right now in our tree. And increment our remaining by 1 and end by 1. So now from root node, we'll search for S, and as we can see that we do not have to make any leaf node for S, so we can change our pointer from root node to the initial S here. I'm going to decrement our remaining by 1. So according to rule 3, if we have reached rule 3, that is we have directly got the character which we were looking for, we do not decrement our remaining pointer. So remaining is gonna be 1 only. Just more I pointer to I, which is at index 4. So as we have incremented our I index, we can increment our remaining pointer 2 and end pointer 2. And as we do in every other step, we have to append I to every leaf node we have in our tree. Now, as our pointer is pointing to S, we see the next character right beside the pointer is S, not I, but we are looking for I. So we have to make a new leaf node according to rule 2 classifier, and that is gonna split into 2. Okay. The index of Si was 3 and was also. Now we're gonna decrement our remaining by 1. Now we will see from the root node if there is any I pointing right directly to the root node. So yes, as we can see from root node, we have an I which is directly pointing. So we have to change our pointer from S to I. So our pointer is now pointing to this I. And as we have reached our rule 3 classifier, that is, we have found the I, we can decrement our remaining by 1, which is gonna be 0. So as our remaining pointer has reached 0, we can now increment our I pointer by 1. So I is gonna be 5, pointing at character S. According to rule 1 classifier, we're gonna append S to every leaf node in our tree. And increment our I and end pointer by 1. Now our pointer is pointing to I, so we can update our 3 pointers active node, which is from root node, and active edge is 1, and active length is 1. So now as we have to find S, we first gonna increment our remaining pointer and end pointer. Okay, so as we have done it already, we're gonna change our pointer from I to S, from this I to S, as we have found the S right next to the pointer which was pointing before. So rule 3 classifier has reached. We're gonna change the pointer. S. So after hitting rule 3 classifier, despite the fact that remaining pointer is not 0, we can increment our I pointer. So I pointer will now point to 6. Index it is character S. I increment our remaining pointer by 1. And pointer by 1, 2. And as we have done in every other step, we are gonna append S to every other leaf node we have in our tree according to rule 1 classifier. Now we will see if there is any S right next to our pointer. As we can see from our tree, we have an S pointing right next to our pointer. So we just gonna change our pointer from previous S to the current S. I wanna change our active length pointer from 1 to 3. So after changing our pointer, we know that we have hit our character which we were looking for. So like I said before, despite the fact the remaining is not 0, we can increment our I pointer. So our I pointer is gonna point from 6 to 7. And like we do in every other step, we're gonna increment our remaining pointer by 1 and end pointer by 1. And append I to every leaf node in our tree. Now we will see if there is any I right next to the pointer which was pointed to S before. As you can see from the diagram, there is an I pointing right next to the S, so we can change our pointer from previous S to current I. Now you can increment our I pointer as our rule tree classifier is satisfied. So increment our I by 1. Is gonna point a dollar sign. And as we have done in before step, we're gonna increment our remaining leaf first. 4, increment our end pointer 2 by 1, it's gonna be 8. Now we will see that the character which we are looking for is dollar and the pointer which is pointing is at I. We're gonna see if there's a dollar right next to I, and as we can see that there is no dollar right next to I, we're gonna make a new dollar leaf. We're gonna split this edge into two halves. According to rule to classify, if we do not find any character which we are looking for, we can make a new leaf node for that character. As you can see, I have made a new leaf node for dollar here, starting at index 8 till end, and SSI dollar, which was right before, starting from 5 till end. And also I have added dollar sign to every leaf node, which are on our tree. And also I forgot to mention that every time we make a new leaf node, we're gonna point it to the root node. So our just name is P directed to root node. Now as we have made a new leaf node, we are gonna decrement our active length pointer and increment our active edge pointer by 1. So, so our active node is root. So from root we can see that we have to move to the edge which has starting index 2 by length 2. So moving from root to edge which has index 2 which is S, and by 2 length 2, so we move from here to here. And also we are going to change our pointer from I to the active edge and active length. So our pointer is going to change from I to this I. As you can see, our root node has changed from R to A. We're going to change it from in the pointer A Now we'll see from the pointer which is pointing to I if there is dollar right next to it. But as we can see, there is no dollar right next to it. We have to split it again according to rule to classify, and we're gonna split it into two halves, one for dollar and one for SE side dollar. Now as our pointer is pointing to I, we're gonna change the active edge, active length, and the remaining. As we have made a new leaf node, we are gonna decrement our remaining by 1. This is going to be 3. We're gonna increment our active edge by 1 and decrease our active length by 1. The reason why we have changed our active edge to 3 is because as our pointer is pointing to I, you can see the starting index of I is 3. So we have changed our active edge to 3, and the distance of I from node A is 2. So we have changed our active length to 2. And of course, the active node is A. So now we are gonna traverse the suffix links which we have created from node A to root node. Now as we have reached root R, we're gonna traverse it through the pointer. As our active edge is pointing to 3, you will see that the index of 3 is S, so we're gonna traverse to S. And as our length is 2, it is gonna be at I. Because the active length is 2, as we can see that the first is IS and the second is I. So we're gonna see if there is any dollar right next to I. As you can see, there is S but no dollar. So we're gonna again split the leaf node and make a leaf node for S and change our pointer from the current I to this I. As you can see, now our pointer is pointing to this I, and we have named this node as D. We have labeled the SSI dollar to pi comma end and new dollar leaves starting from 8 comma n. Now again we are going to change our active edge, active length, and the remaining. As our active node is still A, we are not going to change the active node pointer, but we are going to change the active edge pointer, which is going to point at 4. We're going to change our active length from 2 to 1. The reason being we changed to 1 is because the distance from node A to I is 1. Now, I forgot to link the D to the root node. As we create a new node, we're gonna point it to root node always. So when we made the C node, we have to point it to D, point it to R root node. But as we consecutively we made the second node D, we have to point the C to D. So whenever we made suppose if we made a new node from D, suppose it is called E, then we have to point the D to E. We have to remove it from we have to unlink it from root. Also, every time we made a new leaf node, we're gonna decrement our remaining by 1. So remaining is gonna change from 3 to 2. That means that if remaining is 2, that we only have 2 suffixes to satisfy in our tree. So now traversing back, as our A as our parent node of pointer, which is I, and the node is A, the node is pointing to root node. So we're going to traverse to root node, and then root node we can see from the pointers that we have, that is active edge is 4. So for 4 at index 4, we have I. So we are going to move in the direction of I, and with the active length of 1. So our pointer is going to change from this I to this I. The new pointer is here. I'm gonna erase the old pointer. Now from this pointer, we are gonna see if the next element is dollar or not. As we can see that the next element from I is not dollar, but as we're gonna make a new leaf node from this pointer, I'm gonna divide it into half like before. So let's make a new pointer, leaf node. As you can see, I have made a new leaf node and labeled it E. And now we're gonna change our pointers. As you can see, the pointer is pointing at I, which has a parent node AR. So we're gonna change our active node from A to R, increment our active edge from 4 to 5, and decrement our active length from 1 to 0. And also we are going to decrement our remaining pointer from 2 to 1. Now as we are back to the root node, we have to look for dollar sign from here, because as our active length is 0, we don't care about the active edge, and we can see that from root node there is no dollar sign. So we have to make a new leaf node according to rule 1 classifier, as we have done it in the beginning, that if we do not have any character in our tree, we make a new leaf node for that from the root node. So this is gonna be like this, dollar e comma n. And now, as we have reached our rule 3 classifier, that we have reached the character which we were looking for, we're gonna decrement our remaining from 1 to 0. So as our remaining is changed to 0, now we are out of the loop and our tree is ready. We can check it by taking any suffixes we want. Let us see if we can make suffix like ISSI. So from root node, if you want to make ISSI, we can traverse on the right hand side of the root node ISSI. Yes, we can make the suffix ISSI. Now let us take another random suffix like SI dollar. Let's see if we can make the SI dollar. Yes, we can make SI dollar by traversing below the root node from here, here, and there. Yes, so like this, every suffix are satisfied in this tree. So our tree is ready. I know this is not the perfect visual representation of tree, but with the pen, I try my best to explain the construction of suffix tree using Ukkonen's algorithm. As we have done it with O of n algorithm, O of n time complexity, which is very much efficient compared to any other suffix tree construction algorithm. So like, if we move to the application, there are several applications of substrings. For example, if we wanted to check if the substring is present in any text or not, we can do it with the help of Ukkonen's string suffix tree algorithm. There is a given text string and pattern string exist or not in a text. We can make it use with the use of this tree. Like if you wanted to find if a substring SISS is present or not in a given text, then we can just draw the tree and you can traverse to the tree step by step. Let us say if you wanted to find if the string, if the substring ISSI is present or not, then we can just traverse the tree ISSI. So as you can see that it is present on the tree, then we can say that it is possible to find a substring in a given string. This is like the first example of the Conant's suffix tree algorithm. And the another one is longest bit substring. Like in the example, if you wanted to find which is the longest bit substring in given example, then we can see that here in our example MISSI, you can see that the substring ISSI is the longest repeated substring ISSI, which is repeating 2 times and which is the longest common substring. To make it more clear, the longest repeated substring is gonna be between the farthest internal node and the root node. In our example, the longest is ISSI. As you can see that the farthest node from the root node is gonna be this 3 nodes. It is node C, node D, and node B. And between them, which one is the longest is going to be which is the longest substring is going to be our answer. That is, if we go from root node and check the characters between root node and the node C, we can see that the SSI is what we are getting. So SSI is 3-character repeating node. And if we check from root node to node D, then SI. But as SSI is greater than SI, for now we consider SSI to be our longest. But if we check from root node to node B, then we can see that ISSI is consisting of 4 characters, which is greater than SSI, which we got from the previous comparison. So we can see that ISSI is our longest repeating substring in our given question. So what we understood from this is the longest repeating substring is always gonna be between the root node and the deepest node available in our tree, which is the farthest node from the root node. So if you wanna find the longest repeating substring in a tree in O of n time, then we can do it with the help of Ukkonen's suffix tree construction. That is it. Thank you.